Hi, everyone. Thanks for joining our 17th, or actually, I think it's 19th, 18th maybe, user meeting. Today we have three exciting topics. The first one will be Victor's. He will show us the Diff Studio, an exciting tool, exciting environment for modeling and differential equations. Then Konstantin will show us our work, how we integrated MLflow heavy sort of modeling with Datagrok that would allow data scientists to deploy models directly to Datagrok. And then David will show us some high-tech stuff, how we can run dimensionality reductions, the full-blown toolkit, really quickly, completely in the browser. So let's not waste time, and I will pass the microphone to Victor in a second. Yes, Victor, you are the host now.
Thank you, Andrew. So let me share my screen. Sorry, I have some problem with this. Organizer, I have no permission to share my screen.
So you are a host. Oh no, for some reason Pavlo is a host. Okay, I'm reclaiming the host, and now I'm giving it specifically to you, Victor. Victor, make host. Yes. Probably should work now. Apologies.
Yes, thank you. So I hope you can see my screen. Yes?
Yes.
So hello, everyone. I'm Victor, a data scientist at Datagrok with PhD in physics and mathematics, and today I will show you a very cool feature for modeling complex processes and solving differential equations right in the browser. Datagrok has very powerful tools for scientific computing. Our clients use them to model drug design and manufacturing processes. And there is a set of use cases involving solving differential equations. One of the tasks was to provide simulation of a certain bioreactor process, and that simulation requires solving of a huge system of ordinary differential equations. And our team provided fast computations. Let's check them. Let's go to Model Catalog and run Bioreactor. Here we can see user interface, and a scientist can easily input parameters of simulation, and Datagrok computes simulation on the fly. By moving slider, a scientist can easily explore the model behavior and analyze the particular features of the simulated process. Another use case is pharmacokinetic-pharmacodynamic simulation. As above, we can easily explore the behavior of the simulated process. This approach and these applications provide a scientist with all Datagrok advantages, including fast model exploration, interactivity, sensitivity analysis and parameters optimization, sharing results with colleagues, and so on. And after we created these applications, we decided to create a tool where scientists can enter formulas and automatically get such an application. So no coding, just formulas. And we have created this tool. Let's check it. Let's go to Applications and let's run Diff Studio. Here, user can enter formulas and Datagrok provides computations. Go to the Run tab, and here we can see inputs, and we can easily provide modifications of the simulation parameters and explore the model. Let's modify the equation. For example, let's add some coefficient, run computations, and we have got results. This is a simple model. And check that the only user's job is to enter formulas, and Datagrok provides everything else. And all computations are performed right in the browser. Consider more complex example. Let's open templates and let's consider the following model. As we can see, there are two equations and several expressions, and a set of constants and parameters. Let's go to the Run tab, and here we can see user interface that is automatically generated just using the model specification. Let's modify inputs, remove sliders, and we can see the behavior of the process. When creating the model, user can start from the scratch. Also, user can apply one of the templates. And in addition, Diff Studio has a set of use cases, and these use cases show all capabilities of this tool. There is chemical reactions. We can modify kinetic constants, and we can easily explore concentrations. Also, there is another interesting model, pharmacokinetic-pharmacodynamic simulation. This example shows the dosing feature of Diff Studio. Check that we can easily modify the number of doses as well as vary other inputs. Another interesting example is acid production. This is an illustration of multi-phase process simulation. And again, we obtain computations on the fly. And finally, here is our bioreactor. This is a huge model. There is a lot of equations, expressions, and so on. And this example shows how Datagrok performs a huge amount of computations. Each time we modify input, we obtain some output. But what about the inverse problem? For example, we have some experiment, and the task is to find such parameters of simulation that ensure exactly this output. In order to solve this task, Diff Studio has the following parameter optimization feature. Let's click this Run Fitting icon, and in the open view, we select parameters to be found. Also, we set the desired output. We also set an expected number of points and run computations. And we have got several values. And also we can compare simulation with experiment. We see that simulation is pretty close to the experimental data, and so the inverse problem has been solved. And currently we have found time and concentration inputs. In Diff Studio, there are many other features. In particular, there is the possibility to perform sensitivity analysis of the model. Also, user can easily create Datagrok applications. Just click this export to JavaScript script button, press save. Let's go to model catalog, refresh the view, and here is our new model. And we can explore it, share it, and obtain the desired results. So that is Diff Studio. Check it and dive into modeling with Datagrok. Thanks.
Yeah, thanks for the presentation, Victor. So I have a question. So can you give any practical applications or examples for solving the reverse problem? Why did we have to do it?
So one of our clients has the following task. There was some bioreactor model, and that model has unknown kinetic constants. And the task was to fit that constants to provide good fit of the model. And we have applied this run fitting tool in order to compute that kinetic constants. And in that way, our client obtained pretty good model. So the only user's job is to input formulas, and Datagrok performs everything else, including visualizing numerical solution of the system of these differential equations. Also, it creates a user interface just using model specification. Also, there are several very important analytic tools such as sensitivity analysis and fitting. And also all these can be easily exported to platform scripts, and in this way, user can get the platform application. Also, these models can be shared. So, so if a scientist want to share his result, his or her result with colleagues, just copy URL, share this URL with colleague, and that's it. And in this way, other scientists can explore these results. I hope I answered your question, Andrew.
Yes, you did. Thank you. Yeah.
Yeah, unfortunately, I joined a few minutes later, so I do not know whether I mentioned it already or not. Which method do you use to solve the system of differential equations in this place?
Currently, we use several implicit methods. Currently here we use so-called the modified Rosenbrock method. And here, this is implicit method, and currently it's the modified Rosenbrock triple. And actually, it is this method that provides fast computations, especially when solving stiff problems. For example, Robertson model is classic stiff problem. Yes, and we can see that Diff Studio performs computations on the fly.
Yeah, I'm quite familiar with the subject actually, because about 30 years ago, we had the similar application for solving the direct and reverse kinetic problem, because I'm a chemist by training, so my PhD was on high energy chemistry, and stiff differential equations are kind of common. We had an application that would run on MS-DOS, and look pretty much like this, with much less polished interface, of course.
Yeah, it goes in circles. Yeah, in cycles. Now we have it in the browser, and it's
But we used a slightly modified gear method. for the stiff differential equation systems.
Yep.
By the way, I even have the C++ code somewhere for that solver.
And by the
which
way,
I wrote about 30 years ago.
And by the way, the idea of this Diff Studio, this tool, we started with bioreactor and another interesting model, and this bioreactor also uses C++ code generator. We have created last year so-called web after solver. User just input formulas, then we run special script, and it creates a Datagrok package, which involves C++ code, WebAssembly, package code, and so on and so on. But it was too complicated for scientists. It was for developers, not for scientists. And Diff Studio is for scientists. So a scientist can easily modify these equations. Just go to Run tab, and that's it.
Yeah, what's cool is that we also have a registry, so it's very easy to share your work, either the models or particular runs. Yeah, and also it natively integrates with the rest of Datagrok, so you can use either the inputs as coming from your proprietary databases, or, and that's a popular thing, having a system of differential equations and some simulations. You can pull the real historical data and compare it to the simulation. Yeah, and that yields multiple benefits. So first of all, it checks that the simulations is good or not, so you can act on that. Yeah, then you can solve the inverse problem to find out some real coefficients, because differential equations sort of define the laws of physics and chemistry, and you can find out what the coefficients and things like that. But another thing that another potential application is you can specify the desired end state and find out what are the initial inputs that you can set to arrive there. So you can specify the desired proportions and concentrations of different materials, and yeah, the inverse problem solving would give you the inputs. So maybe,
yeah, it's really it's really cool. Even makes me feel kind of nostalgic, because it's even the language looked very similar for defining a script. And unfortunately, Andrew, I can't really show you the application because it won't run on on modern Windows. It was compatible with like Windows 3.1.
Nice.
Yeah, but the thing was actually processing the initial script with differential equations, all the coefficients and everything, pretty much similar to what you have on generated C++ code, which was dynamically compiled, linked with the rest of the application, and the interface would show the graphics and everything.
Yeah, that's exactly, well, like Victor said, that's exactly the way we did it last year. But that means we need to compile the code.
Yeah.
It was either a long and very involved step on a server. So now what we do is we do it all inside the browser using, in this case, JavaScript with some C++ optimizations for matrix multiplications and so on. And later we have a plan on implementing it using webGPU, and that would probably end up in another 100x speed up. And speed is of huge essence for it. It does not matter that much when you solve one equation, although even here we, I think, improved about 100 times over the original Python model that we worked with. But it really matters when you solve the reverse problem or when you do the sensitivity analysis. So maybe, Victor, maybe you can just very briefly mention what the sensitivity analysis is and how it's applicable to Diff Studio, to the sets of differential equations.
Okay, so let's open that big complicated model. For example, in this case, we see that if we vary this time parameter, let's run sensitivity analysis. Just click this icon. Here in this view, we select inputs to be varied. Just click run. And here we have got PC plot that shows variation of each output. Also, we can see a correlation plot that provides a birdwatch view on the results obtained. And also we can see numerical results and some points, yes, that provides relation with between these inputs and outputs. And by the way, now we have run this model evaluation for 10 times, yes? And we have got results maybe in a second, yes? And that process requires solving, sorry, let me find that equations. And the process requires solving this very huge system. And we obtain, and we can see the behavior of the model, yes, the behavior of a very huge model, and it takes just a second.
Yeah, just for clarity, we solved it probably 100 times right now, and yeah, all of these charts just show how different inputs influence the whole simulation. And yeah, we probably don't have time to dive deeper into that, but I want to mention that all of that is also applicable to arbitrary functions that you can write in Datagrok. So sensitivity analysis and partially solving inverse problem is also applicable to other cases. Yeah, well, yeah, thanks, Victor. That was very exciting. I'm still amused when I see things like that working completely in the browser. Thank you. And now we will move to, for a change, to actually things that work out of the browser. And Konstantin will tell us about our progress with integrating with MLFlow. Konstantin, you are the host.
Yeah, okay. I guess I am. Hello, everyone. Let me click on all the buttons to start sharing my screen. And please tell me if you hear me or not.
Yep, everything's good.
Okay, great. So we can start, I guess. Let me, zoom in. Hello, my name is Konstantin. I'm a software engineer at Datagrok. And today I will be presenting our new improvements in predictive modeling. I will be mostly focusing on our integration with the MLFlow system. And we will have a Q&A section at the end. But if you have questions on the go, don't hesitate to ask them. I will do my best to answer them. So let's start with the story why we need the integration with MLFlow. Because as you know, or you might know, but you will know now, Datagrok supports predictive modeling. So you can see we have models in the toolbox, and I will show you what it does in just several minutes. The issue with our previous approaches was it was not versatile enough for all the use cases. For example, we have one of the clients who run, they run a lot of models that predict different activities of some small molecules. And they have a team of data scientists who develop a lot of applications, a lot of models. They train, they improve the quality, they create new models. And for them, it's a big issue to organize all of it because it's a lot of different data. It needs to be labeled, versionated, and so on. Not only that, but they also had the issue how to integrate it with Datagrok. So all of the users inside the company who use Datagrok, who work with data sets of molecules, can use these models with real data. So they use MLFlow, which is a great system for organizing your machine learning models and other statistical models. And we've provided an integration with MLFlow. So what it allows you now is to, I would say it's like a two-stage process. So your data scientists, they might train your huge model overnight, and by morning, all the coefficients for this model will be calculated. It will be ready to be shipped. And Datagrok automatically fetches this model from MLFlow. So user at the morning, for example, comes to the office, and when they work with a data set, they can just click models, click on ChemProp model, because Datagrok automatically understands that ChemProp-based model is applicable to this data set because it has molecules. You can see that we have some parameters that we can specify, but in this case, they are already automatically assigned because the model that accepts drugs, it expects the input to be a molecule, so we just pass smiles. And now when I click on OK, it will take us, I would say, something around 10 seconds to get the data from the big pre-trained ChemProp model. Let me show you how it looks from the part of data scientists who uploaded. So these values that we got, it's solubility values. It's logarithm of these values. So that's why there are negative if you are curious about it. This data was received from the model that was uploaded to an external service MLFlow. So let me change the tab. And now we are in the MLFlow service where we can see the model registry. That's the registry where you can upload any sort of models. And you can annotate it, you can keep their versions and so on. For example, I've already uploaded several models from Python code. For example, I've built a linear regression based on a scalearn package. Or, for example, with the help of our scientific developer, Alexandra, I've built, she has built the model, and I've managed to upload it to the MLFlow system. So it's a ChemProp-based model that runs computations for solubility inside of it. As you can see, these models are annotated, and with special tags, Datagrok, our system will know that this model needs to be integrated to the platform. And you can also annotate inputs and outputs of model. So, for example, our ChemProp model is annotated in a way that it supports molecules as input. Let me show you a bit more about the interface of the ChemProp model. So when we move to the model view, we can see the text of this model. And we can also get to the latest version of this model and look at the inputs and outputs for it. It's strongly typed, so that's how Datagrok understands what types of columns we can pass to this model. For example, here it receives a drug as a string, and it predicts its solubility as a float. And now I will show you the only thing that's needed from the Datagrok part to connect to it. Let's go to browse. And let's go to platform, predictive models, MLFlow. So in MLFlow, we can set up all the connections to the MLFlow instances. For example, I use one that is on my internal network. I've set up the connection, and this connection is queried every every period of time, and fetches all the models to the system. So now when I click predictive models, I will see that I have several models available in Datagrok. I have ChemProp test, which I've shown you. I also have two sklearn models that are downloaded with MLFlow as well. And I also have a script-based model that I've created with a more traditional Datagrok approach, function approach that we've used before and we still support now. You can see that ChemProp model is applicable to our table with molecules, and our other models, they are numerical models, so they are applicable to the other tables that I have available on the platform right now, table with random floats. I can also, I guess, show how we've improved the matching system. So you've already seen that it supports SEM types, and for molecules, the only thing you need to do is to click to run model and then click OK. But for random floats, you can see that it's not very clear. For example, if we have a model that was trained on some arbitrary data, how to perform mapping between what it expects and what we have in our data set. And we've improved our matching. So now matching runs with respect to names of the columns. So for example, when I ran SK Iris, it's a model that expects only 4 columns, but we have more columns than that. And some of them are obviously extra columns that are not related to the model. But in our inputs, we get the match exactly by the names, but not exactly by the names. You see, they might be different, but we suggest users the most reasonable way to map them automatically. And when we run it, we will get outputs from the model. You can see there, this model was not labeled as solubility. It was labeled as output 0 because when it was uploaded to MLFlow, it was not labeled. So it gives us a new column labeled 0 with the output of the model. That's more or less it about the functionality from the Datagrok side. I can also show you how it looks from the perspective of data scientists, because one of the things you might think right now is, well, this is great, but maybe it's just too hard to do all this integration with MLFlow. And the answer is no, it's not. MLFlow supports all the popular frameworks, libraries, and languages for modeling. So Python, R, different statistical packages, they're all supported. And for example, the model with Solubility based on ChemProp, it's not the easiest model to use by any means, because you need to store somewhere pre-trained coefficients of the model. It requires extra Python dependencies and something else. It's still just a Python script of, I would say, 60 lines of code that includes all the training, all the setup, everything else, and it's easily can be integrated into your data science pipeline. Yeah. So all of that was done so we can easily click on the model, apply model, and get the results on the go when you work with your data sets in Datagrok. Thank you so much for the attention, and I can answer some questions if you have.
It's kind of funny that all chemical examples just love benzodiazepines, you know, this type of drug, you know.
I think it's part of our SAR data set.
Yeah, I've noticed that solubility values are quite quite low, and it probably means that there are something wrong with the molecules that I've took for the test. Yeah, I'm not really good with chemistry myself, so yeah, I've took one of the data sets that were available with molecules, and
Yeah,
yeah, we can see that it's not the good thing to be used as a drug.
no, benzodiazepines are very common drugs, actually.
Ah, okay, then.
Yeah.
They're just very similar, and they're similar because the data set was prepared not for the purpose of demoing on the modeling, but for the SAR analysis. But
So
yeah,
these are very common drugs, like Valium,
Okay.
you know, Clonopin, etc., etc. But can you describe, like, at the high level, if I am to develop a totally brand new model, how would I go about, like, starting the process and registering it and annotating it? What does the workflow look like?
Yeah, sure. So MLFlow supports several statistical packages. I would say it's like 20 to 30 items on the list.
a suggestion, maybe if you just show the code in Python, it's
Yeah, I have it
really
opened.
apparent.
I can comment on it. Yeah, so it might depend on what technology you use. But for example, for Python, I have two scripts available. Let's open the one that uses sklearn, for example. For sklearn, it's an easier one because it's already supported by default by MLFlow. So you create.
If I can interrupt, and Dima, so what Quest is showing is just a script to quickly show. You don't need Datagrok for training. That was the part.
I've lost Andrew.
That was the idea. So we already had scripts inside Datagrok that you can use for training models. But now integration with MLFlow, you can have the whole life cycle completely separate from Datagrok and just connect Datagrok to the MLFlow server. I just want to make that distinction because currently it looks like it's in Datagrok. It's not.
Yeah, the only reason why this code is inside of Datagrok is for the demonstration purposes. So in reality, it was in my VS Code window somewhere outside, and I ran it from my command line. So it's not really relevant to the Datagrok platform. It's it's basically an MLFlow integration. So
yeah, so essentially you just define model in MLFlow, including all the metadata, like inputs, outputs, the types, and everything, and then connect to MLFlow instance, and that's it, right?
Yeah, for the case of a sklearn, that's it. That's exactly like you need to set your URL of your MLFlow instance, and you need to call MLFlow sklearn log model, and that's it. It will set all the data just fine. For example, for a chemprop model, it's a bit more verbose in terms of code, but it's still the same process. I can show you in the separate slide because this is a model that I got from Alexandra. So it uses some additional dependencies. It should be annotated as MLFlow Python model and implement two methods that are common for this sort of model. That's enough for the model to be locked to the MLFlow instance with the same one-line comment, basically. So as you can see, the two things you need is the way to initialize model and the way to predict model. And I assume that every model that you want to use already has this done like in one way or another.
So at which step do you define the inputs and outputs and their types?
So it's done differently for different types of models. For example, this model, it operates on pandas data frames, and pandas data frames, they are annotated, and we get types from MLFlow as well. So MLFlow detects types. The only thing you need to do for this MLFlow model, for this chemprop model to be integrated with like chemistry dataset, is to annotate its SEM type if you want to. But if you don't want to, well, you don't have to. It will be just one of the models on the list, and you will be still able to use it.
So Dima, you can do it either from the Python code, set up this,
or from UI.
Right, or from the MLFlow UI. Yeah, what's also cool is that it's also a system for tracking experiments. So you see all your failed and good models, and then you can choose which one you can push to production, and you can do it either programmatically or from the MLFlow web app, which is actually fine-tuned for that purpose.
So how does Datagrok run prediction? Does it actually send the entire input to the model and then consumes the entire output, or does it run it in chunks?
So I guess there is two things to say about how we run this model. So this model is ran into a Docker container separately inside of the platform. So when we detect that there is a model and that we want to use it, we just start the Docker container that serves specifically this model. And then we query this model not in one-by-one manner, but in batch manner. So for example, if this table was bigger, it's how much? It's 200 rows. If it were, I don't know, 10,000 rows, we would just send the data to model in batches. Yeah, but the MLflow models support batch inference, if you ask about that.
Mm-hmm. Yeah, well, basically I'm asking whether that parameter is defined. So I mean, how the batching is going to be, how granular, how many items per batch are going to be sending. Is it defined in Datagrok or where?
Right now it's defined by us, but we can also support separation by like external parameters from user that define that this model is more or less computationally extensive, and that it can't, for example, accept more than 100 molecules as an input at the same time.
Mm-hmm. All right, looks pretty good.
Yeah, that's one of our efforts in improving predictive modeling. So it's a way to integrate really heavy models that are usually developed to be used in like outside of Datagrok context, but to use it in Datagrok as well. We also are doing a lot of new features for our interactive lightweight models, and I hope we'll show you them on the next user meeting.
Yeah, thanks, Kostya, for the interesting presentation. Yeah, models are pretty useful. We also plan to integrate with other model registers, maybe Hugging Face and others. Yeah, it's an ongoing effort. And yeah, please join us in 3 months, so we'll show the interactive stuff. It's really exciting. So now back to the browser-based stuff. This is what always interesting. And David, you are a host now.
Oh, thank you. 1 second. Yeah, can you see my screen? Yeah, great. Hello, everyone. My name is David, and I am scientific application developer here at Datagrok. And today I'm going to be presenting the improvements and capabilities in dimensionality reduction of Datagrok. So dimensionality reduction generally is a very great tool for visualization and also understanding your data, as it clusters and basically puts your data in 2 or 3 dimensions, which can enable its users to better see how the things are clustered and how is their distribution. And as you know, there are probably lots of tools that do dimensionality reduction, most notably UMAP and t-SNE. These are the two good algorithms that are generally used for this purpose. And there are a number of features that set our implementation apart. As Andrew mentioned, in Datagrok, it's a complete toolkit now, which supports many things. And let's go over them one by one. So first, to use dimensionality reduction, you can go to top menu, ML, and reduce dimensionality. And this will bring up this dimensionality reduction dialog that you see. And the first feature that sets us apart is that we can use different columns. So in general, dimensionality reduction is used on vectors of n dimensions, so a large set of large vectors, but we can support not only vectors and numbers, but also strings, molecules, different biological sequences, dates, and so on. And for each of those, we have defined some distance functions that enable us to later use it to reduce their dimensionality. And the second thing that also is quite unique about our implementation is that we can combine different columns together. So for example, if I go into this column input here, and let me just zoom in a bit, here you can see that we can choose not only one, but actually combine different columns, and we are able to actually combine sequence columns, molecule columns, and some integer or string columns. So for now, let's just choose the sequence column, molecule, and maybe just choose the number column and some string column as well. And when I do that, you can see that I am presented with this table where I can adjust some of the things. And now we come to the next unique thing about our method. It's the extensibility and the modularity of this function, which means that our process is split into four main parts. So the first part is the encoding of each of the columns, which basically means that each column is somehow encoded for later it to be understood by the distance calculations. And what I mean by that is, for example, for molecules, we first need to translate those molecules into molecular fingerprints and then compare those fingerprints in order to construct the distance matrix and basically then use it for dimensionality reduction. And this first column that you see here is exactly that. And this is absolutely context aware. So it understands what type of column it works with and then presents the functions that are basically applicable to that column. And for the sequence, it presented with encode sequences function. And for molecules, it's presented with a fingerprints function. And each of those functions then can be adjusted. So for example, for molecules, I can click on the gear icon here, and I can also adjust what type of fingerprints we are using. And as for similarity goes, the most popular fingerprints to use for comparing similarity are Morgan fingerprints, but we also offer tons of others as well, like Ardekit fingerprints, pattern, and so on. And for the biological sequences, we also offer some choices for alignment. So for example, if we use more complicated distance functions like Needleman-Wunsch, for example, there we can adjust the gap open penalty, gap extension penalty, and also we can construct the similarity matrix of monomers in order to score the match mismatch with not just 0 and 1 like Levenshtein distance does, but actually score them according to the similarity of different monomers. And then we can see that the next inputs are the similarity metrics. These are the distance functions that will be used for comparing the pairwise values of these columns. And for biological sequences, again, we can see that we have options of Hamming, Levenshtein, and monomer chemical distances, and Needleman-Wunsch. And as I said, this Needleman-Wunsch is a more complicated version of Levenshtein, which also takes into account the individual distances of monomers between each other, and also takes into account different penalties for opening a gap or extending a gap. And we support all this as well. And for fingerprints, there are different similarity metrics for bit arrays, which those fingerprints are basically a long array of zeros and ones. And the most popular ones are Tanimoto, asymmetric, cosine, and SOCO. And as I said, we can support just numbers as well, like weight here. And for numbers, it's just going to be difference. And for normal strings, we can do either one hot, or meaning match or mismatch, or Levenstein or Hamming. And next, the last column here is the weight. And as I said that we can support multiple columns, the distances between pairwise values of those columns need to be aggregated somehow. So we use these weights that are supplied from here to aggregate the distances. And the aggregation function is also defined here below, which can be either Euclidean or Manhattan distance. Next, we have the method of dimensionality reduction itself. So by default, it's going to be UMAP, but we also offer t-SNE. And if you want to adjust some of the UMAP parameters, you can also click on the gear icon here and adjust its learning parameters like that. And lastly, the last part is the post-processing function, which basically takes the embeddings and does something to it. So by default, it's going to be a dbScan clustering. And what this dbScan does is basically clusters the closer points together according to their density, and then uses it to color those points. And the result you can see also on the screen here. So and the part that I mentioned about extensibility is that all the functions that I just described are not hard-coded in our dimensionality reduction toolkit, but rather are coming from anywhere in the Datagrok. So just by using any of the, just by using a special tag, any Datagrok user can extend the functionality of dimensionality reduction. And the use case for this is if some of our clients have a specialized column, we can very easily add a support for this column by just defining a function for its encoding and defining functions that support the distance that can calculate the distances in those columns. So now let's just run it. And
can I quickly ask you a question before you
Yes.
close our dialogue? So does the clustering happen in the projection space or in the original distance space?
This post-processing, you mean, I'm guessing?
Yeah, because you can do it on two different ways. Either first you create the projection and then cluster in that space, and in that case it'll be the 2D geometric space, right? Or you do the clustering in the original space defined by the upper part of this dialogue.
No, we
And
do the
results
clustering of the embedding space. So basically, UMAP is one, if we can call it the clustering, but the post-processing part happens to the embeddings. So basically, the input to dbScan is the coordinates of the embeddings.
Because in many applications, actually, better idea to do clustering in the original space defined by your metric, because you lose a lot of information, and geometry may not necessarily reflect the true distances on the projection.
Yes, in one sense, I do agree with that, but that can result in basically then we would have two different algorithms for clustering, and that can then lead to basically members of same clusters being in different places in these embeddings.
Yeah, there's nothing wrong about that.
Yeah, we can do that too. We have also the standalone clustering functionality. So if you want to achieve that, you first cluster and then you actually apply the dimensionality reduction. In this case, it's just a useful one-click post-processing that you can see, okay, I did UMAP and now I want to cluster and color. You are absolutely right, Dima, but we cover that use case, but slightly differently.
Yes, thank you, Andrew. So shall I go on? So let's now, for better demonstration, let's choose the sequence and molecule columns, and let's see how long it will take. This is a relatively small data set, and I'll go on to the bigger ones after that. So let's click on OK. And you can see that the dimensionality reduction is running, showing the progress. And in a matter of a couple of seconds, we see the result of UMAP. Now, this is all good, but we didn't stop there, obviously. And at Datagrok, we love when things run very fast, and we love performance. One of the use cases for some of our clients is much larger data sets. And as you probably know, dimensionality reduction grows, the time taken for dimensionality reduction grows with the square of number of rows. So if it took a couple of seconds for 1,000 rows, for 1 million rows, then it would take probably days or something like that. And for this, what we did was we implemented all the calculations that I just mentioned, including the nearest neighbor calculations that are using the pairwise distances. So for 1,000 rows, it does basically million comparisons between all of those pairwise values, and for million, that would be a trillion comparisons. All that, including UMAP and other algorithms, we rewrote all this in webGPU, which basically lets you use your graphics card on your computer directly from the browser. So now let's see that in action. And here I have a data set of some peptides, which is about 100,000 rows. And let's go back into this dimensionality reduction dialog. Let's choose the sequence column. And under the parameters for UMAP, there is a checkbox which says use webGPU. And it also in the tooltip shows what kind of GPU is available. Now, I should mention that this checkbox is disabled by default, as this technology is still experimental. This webGPU is quite new, but in future we will make this option enabled by default, because it makes things way faster. So, and also to see the speed of dimensionality reduction alone, I'm going to disable the post-processing, and let's click on OK and see how long it will take.
So while it is running, I know this is almost the same size as in our client. So how long did it take previously?
Previously, it could end up taking a couple of hours, actually. And now I would say that RTX 360 is quite commodity graphics card. And even on commodity graphics card in your browser directly, now it takes less than a minute, couple of seconds, actually. And what's even more cool is that we support all those complicated distance functions that I've just mentioned, including ones with alignment, including ones with custom distances between individual monomers, and so on. So as you saw, this is an artificial data set, by the way, with 50 defined clusters, each defined with a specialized motif. You can see that this clusterization indeed resulted in 50 quite distinct clusters. And what this then enabled us to do is that all the things that were using dimensionality reduction as its core, like sequence space or chem space, if you are a Datagrok user, should be familiar with those, and also other things like activity cliffs. It enabled us to also rewrite those in webGPU. And I can also show that on a little smaller data set. So for example, this is 30,000, relatively small. And I can go into bio, activity cliffs, choose the activity column, and similarly under the UMAP, I just check this checkbox, and let's just set the threshold to 90 and click OK. And what this will do is, including the UMAP, the sparse matrix calculation for the activity cliffs is also done on webGPU. And also in a couple of seconds, you are presented with the result of activity cliffs. I can just zoom in and also see the individual lines that go between the cliffs. And I should also mention that we have another clusterization that we also rewrote in webGPU, which is Markov clustering. And this is also very useful and very good visualization, which is available under cluster and MCL. It is very similar to activity cliffs, but it basically arranges the points according to their connectivity and does the Markov clustering. And here we also reuse the same dialog components and same components that we use in dimensionality reduction that enable us to use multiple columns, combine them, and so on. And for demonstration, let's just choose a sequence here as well. And let's set the similarity threshold to, say, 90. And I also check the use webGPU. And I click OK. And here is the result. For now, I chose the quite high similarity threshold, which resulted in much smaller clusters. But you can see that this kind of visualization and clustering can be very useful for your data as well. I guess that's it for my part. I would be very happy.
I recognize that use case. I remember it was running, I think, 4 or 5 hours. So that particular, or a very similar data set of 40,000 peptides.
Yes.
With server-side processing and everything, you had to provision resources, set up jobs, and then somehow distribute to scientists. And now you can do it interactively with 1 click and 2 seconds. Yeah.
And yeah, as you mentioned, there are some available options, but I'm not aware if there are any that allow you to do as many things together as ours. And also the ones that can run on GPU, they don't allow the use of these complicated distance functions, which are applicable to molecules, macromolecules, and so on. So in that sense, our toolkit is quite unique.
Yes, to the best of our knowledge, it's the most comprehensive and definitely the fastest toolkit for dimensionality reduction for life science, small molecules, and peptides. So yeah, we will be publishing a paper on that.
So which part of the calculation is actually delegated to the GPU?
Everything, pretty much everything. So including the basically here are 2 bottlenecks. The one bottleneck is the pairwise calculation. So in my previous example, I had 100,000 peptides, and those need to be compared everyone with everyone. So that results in 10 billion comparisons. And each of those 10 billion comparisons then like each comparison is quite complicated function in case if you use like alignment distance functions like Levenstein or Needleman-Munch, and this is also delegated to webGPU. We have written basically everything in this webGPU shader language, and the things that encode the sequences in order for it to understand, because GPU only understands numbers basically. And then we have also rewritten the whole UMAP algorithm, including its initialization and the learning loop itself to the webGPU. So it's completely in webGPU.
All right, we need to like play with it a little bit. I wonder if our local installation of Datagrok has that feature already.
I think it should be, because it's not a part, like it's a part of Datagrok package EDA. So if you have the latest version of that, that should be there.
Yeah, I'm pretty sure it's there on J&J. So yeah, Dima, you can play with data sets. Yeah, ML, reduced dimensionality. Yeah, make sure you check the webGPU box. Even on the built-in internal adapters, it's a lot faster than CPUs. And first we did it on CPUs with multi-threading and web workers, but GPUs is a couple of steps, orders of magnitude faster.
Yes, and I forgot to mention that, as Andrew said, the without webGPU implementation is running on web workers, multiple web workers, so it's parallel. And I wouldn't say that it's slow. It's actually quite fast, but this takes it to another level.
It'll be kind of interesting to look at the task manager while the calculation is being run.
I can show you actually. I can rerun it, and so let me do this.
Yeah, you will have to make sure that the task manager stays on top of all other windows.
Yeah, no problem with that.
It also has the GPU.
Yeah, there it is. It's. Can you? Oh, I'm not presenting, or?
Oh, you are.
Yeah, I can see it.
Okay, good. So let's see. So let's click on sequence. But actually 30,000 for GPU is very not like light load, I would say. So I'm not sure how it will be seen here, but it will probably jump somewhere. Oh, I didn't check the use webGPU button. Oh, I'm sorry. So let's see sequence. And
how do you cancel a running calculation, by the way?
If you close down the viewer, it cancels the calculation. So when you edit the viewer, so let me just do this. You can see that this updating is here, and if you close the viewer, it will automatically close the calculation. So as I said, the 30,000 is quite light for even 3060, but if I do it on 100,000, let's do it here. So sequence.
Yeah, 100,000. I remember it sounded insane when we started it.
Yeah, there. So okay. Even that cannot reach 100%. So this first spike is the pairwise calculations, and the second spike is the UMAP.
Mm-hmm. Mm-hmm. Yeah, it looks pretty cool.
Thank you.
Okay,
hopefully we already have the latest version installed, and so we can play with it.
Oh, absolutely, yeah. Play with it. Let us know. Yeah. By the way, yeah, David is coming to the USA in 10 days, I think, until September. So we'll see in person. We'll have the ability to play with it. Okay. Thanks, David. Great presentation and fantastic work on the dimensionality reduction. Yeah, very proud of what we achieved.
Credit where it's due. I should say that it was not only me. So, Dima, thank you as well.
Yeah, but I think combining the dimensionality reduction with clustering in the original distance space would be a good idea instead of post-processing, do like combination, because for clustering you also need to compute pairwise distances.
Yes,
and the clustering is much more precise if you do it in the original multi-dimensional pseudo kind of space.
Yeah. So the thing there is that for UMAP and t-SNE, they underneath they use the nearest neighbor graph. So as you probably understand, calculating the whole distance matrix for 100,000 rows is quite undoable in browser, because that would only take 40 gigabytes. Or something like that. So what we do on webGPU is this multi-threaded manner is calculate this KNN directly. and then use it for that. In case of embeddings, this dbScan is actually also quite optimized, as in it's written in C++ and it runs in WebAssembly in browser. Underneath, it basically calculates the distances in 2 dimensions when it needs to, because these calculations are very easy to do. Well, in easy, I mean fast to do.
Mm-hmm.
So
yeah, what I'm saying is that the clusters based upon the original space are much more informative.
Yes, I do agree with that.
And it's perfectly fine if you have a plot where you have members of different clusters in the same visual cluster. It's just like a nature of losing information, you know, when you do the reduction.
Yes, I do agree with that. And yeah, as Andrew mentioned, in that use case, I guess we can reuse a generated clusters from other function, like separately. But yeah, I guess we can make that option available as well to run the clustering on the KNN as well.
Because you define your all your distance metric, you know, the combination of different columns from which some kind of pseudo points and some kind of imaginary space are produced, and then you define the weight to combine them, and it will be kind of logical to use exact same combination to cluster the points. Yeah. So that the user wouldn't have to select the same thing in 2 different places more than once, you know. So you're just like, okay, I use this for visual dimensionality reduction. I use exact same combination of features and weights for clustering in one step. It may actually, if it's easier to implement and the calculations are sufficiently fast, you may just run, instead of storing the matrix, distance matrix. Obviously, it's not possible for large data sets because it's squares, you know. But if you just if the calculations are very quick with all the optimizations that GPU use, you can just perform them sequentially and without reusing the intermediate results, but basically just using the same space defined by user.
Yeah, that can be done.
I think
as
it
well.
makes sense.
Yeah, it does. It does, absolutely. Just as I said, it's like in that sense, as you said, like your use case makes a lot of sense, but the one we have also sort of makes sense for better visualization and separation, basically on this 2D. Because if we use then this UMAP to interpret our data and understand it, then we better basically draw conclusions from that as well. So yeah, so why not offer both, I guess?
Yeah, might as well add pre-processing. All right, any other questions, ideas? Okay, with that.
Well, the traditional one, have you fixed the table join?
I think so, Dima.
I will check, you know, because it's been an issue for since the inception of Datagrok, I think.
Yeah, let me know if it's not fixed. I think it should work. All right. So yeah, with that, I want to thank all the presenters. Yeah, for great work, great presentations. Thanks also everyone for stopping by. We hope to see you next time in 12 weeks from now. We have a couple of exciting topics which we will announce, I think, in a month. So there will be agenda.
Oh, I almost forgot. I wanted to ask a question and I totally forgot. So with the models, the current implementation works on the assumption that you have one input tuple or row in the table corresponding to exactly one output from the model. But there are some models that can produce a variable number of results per input item. How would you deal with that? The most common in chemical applications is, I suppose, your model computes low energy conformations of input molecules, in which case you may have multiple outputs and variable number of outputs per input. How would you handle that?
We have so we have annotations for models, basically, where you can define what you expect to be the input and the output of the model. I guess in the case of when number of parameters vary from run to run, from input to input.
It's not the parameters; it's the number of outputs per input.
Yeah. So in that case, if you know the maximum number that is that can be produced by the model can be annotated with the maximum number of parameters, and then to show that some parameters were not produced by the model, Datagrok supports some values that act as null values for numeric columns, for example.
Yeah, because this eventually you will encounter such cases.
Absolutely. And
certain types of models.
We run predictive models for ADME properties too. So that's another great example with multiple outputs. So I think will be supported soon. So Kostya, we just annotate more outputs, right? In terms, in cases when model produces more than one.
Yeah, of course, we support multiple outputs. That's the case. It is the case. And if it's a variable number of outputs, we can annotate the maximum numbers that we can expect, and then we can just go from the assumption that if something is not produced by the model, then it's null.
Yeah, I don't even know whether you have a cell type on Datagrok, which is an array of items.
We have a cell type which is a data frame which covers an array of items. Yeah, if it's one.
Yeah. So can you have, say, in one cell, can you have multiple molecules?
Yes. They might not be rendered. Well, they will be rendered if you click on a cell. Then in the context panel you'll see the value. But yeah, data frame is one of the supported cell types for data frame, which is pretty convenient. So unlike vectors and lists like we did on 3DX, it's data frames. I think it's more generic.
Is it a data frame in the sense that's a pandas data frame, or it's a data frame structure that basically emulates this on Datagrok?
Well, I was talking about the Datagrok data frames. So yeah.
Datagrok data frame. Yeah, I sort of thought you were talking about pandas data frame. I was like, how the hell it's supposed to work in there? Yeah, so it's data frame is defined by the internal Grok API.
Right. Yes. Yeah.
So you can have nested tables essentially, right?
Exactly.
All right, that's cool. So I'm gonna check it. The first thing I'm gonna do is to check whether the emergent tables has been fixed. Because I use that function often and it sort of never worked correctly the way I wanted it to work.
I think we did some work on that half a year ago. Okay, we'll make it work. I think it should already. All right. I think if there are no more questions. thanks everyone. I'll see you in 12 weeks with yeah, more exciting topics. Okay.
Bye-bye.
Bye.
And bye bye.
Goodbye.
All right, take care.
Right.